Hi, I'm Rob, and I'd like to welcome you to this video where we'll look at evaluating RAG pipelines in AI agents. In the last few videos in the playlist, we built a RAG pipeline, packaged it as an app, and added an agent on top. But so far we've been eyeballing whether it works. We run it, read the output, and decide if it looks about right. In this video, we'll build a complete evaluation suite for those systems. You'll learn how to create a golden dataset, measure retrieval quality with precision, recall, and mean reciprocal rank metrics, evaluate generated answers using both semantic similarity and LLM-as-a-judge, and diagnose agent failures by measuring tool routing and end-to-end quality separately. Now, before we get into the code, I want to look at the README, and specifically the prerequisite section. Here, you'll see you need an OpenAI API key. So if you don't have one yet, head on over to platform.openai.com/API-keys, sign up, then follow the docs to create your key. You'll need to put it in the .env file in the demo folder, as we'll see shortly. And there's also a reference to the tools Python file used in the last video in the playlist. And if you haven't watched that video, I recommend doing so because I walk through the contents of this file and how it's used. Okay, with all that out of the way, let's set up our environment and launch Jupyter Lab. Now in a terminal, go ahead and run the command to create your virtual environment. I'm using UV, but feel free to use whichever package manager you like. Then activate it. Here's the requirements text file we'll install with this command. Then execute this command to register the virtual environment as a Jupyter kernel so you can launch the notebooks with this kernel. Then make a copy of the .env.example file, save it as a .env file, and add your OpenAI API key. And finally, launch Jupyter Lab. So this video is about evaluating the quality of RAG pipelines in AI agents. It replaces the looks right to me validation we used in the prior videos in the playlist with a repeatable, automatable process. But before we can measure quality, we need to define what correct looks like. And to do that, we'll use a golden dataset, which is the focus of this first notebook. A golden dataset is a small set of questions with known correct answers that you create by hand. And it's created by hand because if you were to ask the model to generate its own test cases, you're measuring the self-consistency of whether the model agrees with itself, not whether it's actually correct. Ground truth has to come from somewhere the model can't cheat against. Now, before we start running the code in the notebooks, I want to draw your attention to two files in the data folder. AI agent ensure.md, which is a markdown file containing the source document we'll chunk and load into a vector store, and golden dataset.json, which, as the name implies, contains the sample questions and correct answers for the golden dataset. The dataset is written in JSON and contains an array of object literals with properties for ID, which is a unique ID for the test case, question, which is the user question used as input, expected answer, which represents the answer to the question used to score correctness, which are chunk indices that should be retrieved for this question and used in the retrieval evaluation. Expected tools are the names of the tools the agent should call for this question, and category, which is a label for the test case, like product info, pricing, RAG, or multi-tool. And you'll notice that the relevant chunk ID arrays for each question are currently empty, because in order to populate them, we need to build the RAG index, then print the chunks with their IDs. So we can select the appropriate chunks for each question, and we'll do that in the notebook shortly. But for now, let's run the code in a setup cell. Here we'll do our imports, then call load.env to load the OpenAI API key from the .env file, instantiate an instance of an OpenAI client, set our model to GPT-4o mini, and the embedding model to text embedding 3 small, and finally create a variable to hold the path to the AI agent ensure markdown file. Now, before we build the RAG index, we need to understand how these systems can fail. A RAG or agent system can fail in 4 different ways, and each one needs its own kind of evaluation. First is bad retrieval, where the system pulls the wrong chunks, so the right answer never even makes it into the context. Second is bad generation, where the right chunks are there, but the model gives a wrong answer. It ignores or misreads the context. Third is bad grounding, where the model says something that isn't supported by the retrieved context. It's making things up. And fourth is bad routing, where the agent calls the wrong tool or passes the wrong arguments. And all this matters because if you only measure the whole system end to end, you'll know something's wrong, but not where. Evaluating each layer separately tells you exactly where to fix it. Now let's move down and build the RAG index so the golden dataset is grounded in the actual document. And this is the same code we used to build the index by loading and chunking using sentence chunking in the prior videos in the playlist. So we'll define the load and chunk function, which takes a path to the markdown file and returns the chunks. Then we'll call embeddings create on our OpenAI client, passing the embedding model and the input chunks, and then getting the embeddings from the response data. We'll create an instance of a ChromaDB client and call create collection on it to get the ChromaDB collection, then add the IDs, the embeddings, and the chunks. So let's go ahead and run this code. And we see 34 chunks were loaded. Now we could go ahead and print the chunks with their IDs so we can identify which ones are relevant for the questions in the golden dataset. And here we see the list of chunks with their IDs. So what we need to do now is go back to the golden dataset and fill out the relevant chunk IDs for each question. And we'll do that by looking at the question, where this one is asking about agentic AI liability insurance coverage, then go back to the chunks and search for agentic AI liability insurance. But to make this easier, I'm going to go ahead and copy this output and paste it into a new file in Cursor, view this side by side, which will make this easier for us to see. So let's go ahead and copy the liability insurance and search for it. And we see this is chunk ID 26. So we could jump into the golden dataset JSON file, and for this question, add the chunk ID. And then we'll do something similar, finding keywords in the rest of the questions and adding the appropriate chunk IDs, which as you see, I've done here. Notice that for question 5, we found 2 relevant chunks, same for question 6. And for the multi-tool category questions 9 and 10. Now let's go ahead and save this file, jump back into the notebook, and we can load the golden dataset from the JSON file, which we see here. We've loaded 10 questions with their question ID, expected tools, and the question. Now for our dataset, 10 questions is good enough. But what you really want are realistic questions with verified answers that provide coverage across all failure modes and question types. Now let's go ahead and run this cell to inspect the dataset by category. And here we see we have an even distribution of questions across the categories, and 2 questions that require multiple tools. So now that we have our golden dataset created, we can move on to the second notebook, which will use the dataset to evaluate the retrieval layer in isolation before the LLM ever sees the context. So let's get started by running the setup cell, which now includes a golden path variable with the path to the golden dataset. Then we'll load the golden dataset into a golden variable and then retrieve the questions with relevant chunk IDs, which we see are the 10 questions in the golden dataset because we populated all the relevant chunk ID properties. Now we'll go ahead and do the same sentence chunking we did before to build the ChromaDB vector store. And now we can test the 3 retrieval metrics. But before we do that, we need to understand 3 metrics. They're all about comparing what we retrieved with what we should have retrieved using the golden dataset. So the first metric is precision at k, which answers of the top k chunks we returned, what fraction are actually relevant. If we ask for 8 chunks and only 4 of them are in the set of relevant chunks, precision at k is half. High precision means we're not filling the context with junk. The second metric is retrieval at k, which answers the question of all the chunks that are relevant for this question, what fraction did we get in the top k? So it's the same number of hits, but we divide by how many relevant chunks exist, not by k itself. So if there are 2 relevant chunks and we got both in the top 8, recall is 1. High recall means we're not missing important chunks. And the third metric is mean reciprocal rank, which focuses on where the first relevant chunk shows up. MRR is often the single most useful number. If the first useful chunk is usually at the top, MRR is high. If it's often buried, MRR is low. So together, precision tells you how clean the retrieve set is, recall tells you how much you've missed, and MRR tells you how good the ranking is for the first hit. We'll use all 3 of these when we run the evaluation in the next cells. So here we've defined a precision at k function, which takes the retrieved IDs and the relevant IDs and calculates the hits. Recall at k also takes the retrieved IDs and the relevant IDs, and if there are no relevant chunks returned, it will return 0, else it will calculate the hits. And reciprocal rank takes the same inputs, and if the document ID is found to be relevant, it will return 1 divided by the rank, else it will return 0. So let's go ahead and load these functions. And now we'll test retrieval eval at k equals 8. So here we have a retrieve function, which takes a query, and k, which defaults to 8. It'll call create on the client embeddings, passing the embedding model and the query as the input, get the query vectors from the embeddings data embedding property, and get the results by calling query on the ChromaDB collection, passing the embeddings and the number of results, which is k. Then return the result IDs. So here we're setting k to 8, and we have a results table variable. Then for each case in the retrieval cases, which we defined above, we'll call retrieve, passing it the question, and k. Then call precision at k, passing retrieved, the relevant chunk IDs, and k. Then call retrieval at k, and reciprocal rank. Then we'll append to the results table the ID, the question, the precision, recall, and reciprocal rank, as well as what was retrieved and the relevant chunks. So let's go ahead and run this code. And we see the results for each question ID. Now we can calculate and print the aggregate results for these metrics, which we see here. And looking at these numbers, we see that the mean precision is about 12%. So on average, only about 1 of the 8 retrieved chunks is relevant. So the top 8 is mostly irrelevant, meaning the context you'd send to the LLM is noisy. Mean recall is telling us that we're getting about 65% of the relevant chunks somewhere in the top 8. So we're missing some relevant chunks on a fair share of the questions. And the reciprocal rank of 70% says the first relevant chunk usually appears near the top, often ranked 1 or 2. So the ranking is decent. When something relevant is retrieved, it tends to be early. So overall, these metrics are telling us that retrieval is ranking reasonably well, so a good reciprocal rank, and finding a majority of the relevant chunks, which is an okay recall, but filling the rest of the top 8 with irrelevant chunks, so it's low on precision. So overall, this means that the right content is often there and near the top, but mixed with a lot of noise. Next, we'll move on to comparing 2 chunking strategies. We've already defined a function to chunk by sentences. If we scroll up, in this load and chunk function, which we've already called, passing it our input data. And now we have a chunk by tokens function, which if you watch the prior videos in a playlist will look familiar to you. So here we'll declare a variable for token chunks, which is equal to calling chunk by tokens, passing it the path to the data, a window of 50, and an overlap of 10. Then we'll build the second response by calling create on the client embeddings, then getting the second set of embeddings, and create a second ChromaDB collection, and add to the collection the IDs, the embeddings, and the documents. So let's go ahead and run this cell. And we see the results. And now, if we have retrieval cases, we'll get a sample of the retrieval cases and its question, then create embeddings and get the vectors. Then we could call query on the first ChromaDB collection, getting the sentence chunk results, and call query on the second ChromaDB collection, getting the token chunks. So let's go ahead and run this cell. And we see for the question, what does agentic AI liability insurance cover? For the top three in the sentence chunking, we see the results, as well as the results for the token chunking. So in summary for this notebook, when precision at k equals 1, every retrieved chunk was relevant. When recall at k is 1, every relevant chunk was retrieved. When reciprocal rank is 1, the first retrieved chunk is always relevant. And if less than 30%, the relevant content is consistently buried, so your retrieval needs work. Now let's move on to the third notebook. So in this notebook, we'll evaluate the generation layer. Once retrieval has handed the model some chunks, does it produce a good answer? And we'll do that in two ways. First, we'll use semantic similarity, where we compare the model's answer to the golden expected answer using embeddings and cosine similarity. There's no extra LLM call for scoring, it's just embeddings. A score near 1 will mean the answers match in meaning. Below about 60%, they're meaningfully different. The second evaluation we'll do is using LLM-as-a-judge, where we ask another LLM to score each answer for faithfulness. Is every claim supported by the context? And for relevance, does it actually address the question? This doesn't need a reference answer, so it's useful when you don't have one or you want to understand why an answer is bad. So to get started, we'll run our familiar setup cell, then build the RAG pipeline as we've done before with our load and chunk function, setting the chunks by calling the function, passing the data path, getting a response by calling the create method on the client embeddings, and then getting the embeddings. We'll get a ChromaDB client and create a ChromaDB collection, then add the IDs, embeddings, and chunks to the collection, define our retrieve function and a generate function, where we'll pass the question and the content chunks, then build a message for the system role, setting the content to "You are a helpful assistant for AI Agent Ensure," answer the question using only the provided context. If the context doesn't contain the answer, say so clearly. Then for the user role, we'll pass the content, injecting the context and the question. We'll get the response calling the chat completions create API, then return the message content. And here we define a RAG function, which takes the question, calls the retrieve function passing the question to get the content chunks, then calls generate, passing the question and the content chunks to get the answer, and returns both. So let's go ahead and load these functions. And now we can run our first test with semantic similarity search. So here we define a cosine similarity function, which will return the similarity, and a semantic similarity function, which will return the result of calling cosine similarity with the embeddings for the data. Now we can get the semantic similarity score by passing two similar queries, as well as passing two different queries, and then print the results. So let's go ahead and run this. And we see that the similar sentences have a 97% similarity, and the different topics is significantly lower. Now here we're going to go ahead and load the golden dataset. And for each case in the golden dataset, we'll get the actual answer from the data and compute the similarity by calling the semantic similarity function, passing the actual answer and the expected answer. Then we'll append the result to our similarity results list, giving it the ID, category, question, similarity score, the actual answer, and the expected answer, and print the results. So let's go ahead and run this cell. And we see the similarity scores for our 10 questions with a mean semantic similarity score of around 78%. Now we'll inspect a low scoring case by getting the minimum value from the similar results, setting it as the value of the worst variable, and printing some metrics. So let's go ahead and run this cell. And we see the lowest similarity score was around 67%. For question 6, what does autonomous systems and robotics coverage include? We see the expected answer, and that the actual answer indicates that the context doesn't provide specific details on that coverage. Now we'll use LLM as a judge. In this approach, we don't need a reference answer. The LLM as the judge only sees the question, the retrieved context, and the model's answer, and it scores two things. Faithfulness, which asks if every claim in the answer is supported by the context, which will catch hallucinations, and relevance. Does the answer actually address the question? Each dimension is scored from 1 to 5. We'll ask the judge to return JSON so the scores are always machine readable, and we'll run it over the golden dataset and look at the averages and the judge's reasoning. We'll start out by declaring a prompt for the judge. We'll ask it to score the answer below on 2 dimensions, injecting the question, the context, and the answer, and then tell it to score each dimension from 1 to 5 on faithfulness and relevance, and then respond with JSON. Here we'll define an LLM-judge function, passing the question, the context chunks, and the answer. We'll build the prompt from the judge prompt, and then call the chat completions create API, passing the model and the message for the user role, setting the content equal to the prompt, and the response format to JSON object. Then we'll return the content. So let's go ahead and load this cell. And now for each case in the golden dataset, we'll get the actual answer and the content chunks by calling the RAG function, and then the scores by calling the LLM-judge function. Then we'll append the results to the judge results list and print the metrics. So let's go ahead and run this cell. And in the results, we see that the average faithfulness is 4.6 out of 5, and the mean relevance is 4.3 out of 5. Now let's print the judge's reasoning for every case to understand what it's measuring. And for each question, we see the faithfulness and reasoning score, as well as the question and the judge's reasoning. So LLM-as-judge is useful, but the judge model can fail in predictable ways, and it helps to know them. Sycophancy means the judge gives high scores to answers that sound confident even when they're wrong. Position bias means it favors whatever answer appears first in the prompt, so you can mitigate by randomizing order or averaging 2 runs. Verbosity bias means it tends to reward longer answers. You can push back by telling the judge in the prompt to penalize unnecessary length. And self-consistency is when the same model that generated the answer also acts as a judge, which can inflate scores. So use a different, ideally stronger model as a judge. Here, we'll run through a quick demo by feeding the judge a clearly hallucinated answer and show that it gets a low faithfulness score, so you can see the judge catching something that isn't in the context. So we'll create our hallucinated answer, saying AI Agent Insure offers a 50% discount for startups in their first year, and all policies include free legal representation in any jurisdiction worldwide. Now we'll get the first case from the golden dataset, call RAG, passing it to question, and then get the scores by calling LLM-judge and print the results. And here we see for the first question, what does agentic AI liability insurance coverage, against the answer that AI Agent Insure offers a 50% discount for startups, has a score of faithfulness equal to 1 and relevance equal to 2. Where when faithfulness is equal to 1, the answer is treated as mostly a hallucination. Almost none of what is said is supported by the context. And relevance of 2 indicates the answer is somewhat off topic. It's loosely about AI Agent Insure, but doesn't really answer the question. So this response is largely made up and only partially on topic. That's what you want to see for a deliberately hallucinated answer, low faithfulness and modest relevance. So the demo is working as intended. Now let's move on to our final notebook. So in this final notebook, we're going to evaluate the agent from the last video in the playlist, the one that can call tools like product info, pricing, and eligibility. We'll measure it in 3 ways. First, tool routing. Did the agent call the right tools for each question? We'll compare the tools it actually used to the expected tools in the golden dataset. Second, argument correctness. When it did call a tool, did it pass the right arguments? That's where wrong parameters show up. And third, end-to-end answer quality. So using the same semantic similarity idea as in Notebook 3, we score the agent's final answer against the expected answer. Routing and end-to-end can disagree. For example, perfect routing but a bad answer, or opposite. So we need both to see where things failed. We'll rebuild the same agent, run it on a golden dataset, score routing and end-to-end, and then walk through how to diagnose a failure and tie everything back to the 4 notebooks evaluation stack. And before we start executing the code in the cells, I just want to mention again that this agent is the same agent that we created in the last video in the playlist. So if you haven't watched that video, I recommend doing so because you get a detailed walkthrough of the code for the agent. So we'll start by running our setup cell. Define the load in chunk function and the chunks, the response and the embeddings, get our chroma DB and the collection, and add the IDs, embeddings, and document chunks to it. And define a search docs function, which will give us the query embeddings and the query vectors, as well as the results by calling query on the chroma DB collection, passing the query vectors as the query embeddings, and setting the top K. Then we'll define a search docs schema, which is of type function. The name is search docs, pointing to the search docs function. We give the agent a description of when to use it. It has parameters with properties of query, which is required. Now we'll set all schemas and all functions and define the system prompt for the agent. Now let's go ahead and run this cell. And we see the agent is ready with 4 tools: get product info, get pricing estimate, check eligibility, and search docs. Now here's our run agent function, where we set the message for the system and user roles, and then traverse the max iterations we passed in, each time getting response by calling the chat completions create API, passing the model, the messages, and the tools equal to all schemas, and tool choice set to auto, allowing the agent to decide whether to use a tool or not. We'll get the choice from the response and append the choice's message to the messages list, then check to see if the finish reason is stop, and if it is, we'll return the message content and the trace. If it's not stop and the finish reason is tool calls, then for each tool call in the messages tool calls, we'll get the function name and the arguments, then invoke that function from all functions, passing the args and getting the result. Then we'll append the result to the trace, and of course update the message with the role of tool, the tool call ID, and the content equal to the result. So let's go ahead and run this cell. Now with the run agent function loaded, we can test the tool routing accuracy. So we'll define a routing score function, which takes the actual tools and the expected tools from the golden dataset. We'll create sets for the actual tools and expected tools, calculate the precision and the recall, and then return. So here we'll load the golden dataset, and for each case in the dataset, we'll call run agent to get the answer and the trace, then get the actual tools from the trace, then call routing score, passing the actual tools and the expected tools to give us a score. Then we'll append the results to the routing results list, and finally print the results. So let's go ahead and run the cell. And we see the results for the expected routing and the actual routing for each question. And if you look at question 9 and 10, which use multi-tool, we see the multi-tool routings are accurate. Now for end-to-end answer quality, the agent will use the same semantic similarity from Notebook 3 to score the agent's final answer against the expected answer. Here's our cosine similarity function and semantic similarity. Then we'll traverse the routing results, getting the golden entry, the similarity score, and the end-to-end results, and print the response. So let's go ahead and run the cell. And we see we have a mean routing score of 1 and a mean end-to-end similarity score of around 85%. Now we'll run this cell to diagnose failures, where we'll traverse the end-to-end results again, setting the routing OK variable to true if the result score is equal to 1, and the end-to-end OK variable to true if the end-to-end score is greater than or equal to 75%. Then we'll check those variables and print the response. So let's go ahead and run the cell. And we see that for question 9, there was a generation failure. It used the right tools but produced the wrong answer. with an end-to-end similarity score of 62%. So looking at the three diagnostic patterns, routing and end-to-end scores can combine in 4 ways, and each points to a different fix. If both routing and end-to-end are good, you have a pass, no changes needed. If routing is good but end-to-end is bad, the agent is calling the right tools but the final answer is wrong. That's a generation or prompt issue. If routing is bad but end-to-end is good, the agent got the answer by luck, wrong tools or wrong arguments. And it'll likely fail on harder cases, so you need to fix routing. If both are bad, you have a routing and generation problem. Fix routing first, then recheck generation. That's why we measure each layer separately. End-to-end alone can hide routing bugs that only show up on harder questions. So in this last cell, we'll bring it all together. We report the main numbers, total test cases, mean routing score, mean end-to-end similarity, and how many cases are full passes. In other words, routing is correct and end-to-end is above a threshold like 75%. This is your baseline. After any change to the agent, tools, or prompts, run this again and compare. If a number drops, you know something regressed. If routing and end-to-end both move in the right direction, you've improved the system. The evaluation suite from all 4 notebooks is this baseline. Run it before and after changes to see if things improved. Now let's go ahead and run this last cell. And there's the baseline. So that concludes this video on how to evaluate RAG pipelines and AI agents. If you found it useful, feel free to give it a like. And if you'd like to be notified when I add more content to the channel, please consider subscribing. Thanks for watching.